So this is my favorite topic for this chapter. It's dealing with chaos and chaos theory. So just a couple things to review. You want to remember, first law of thermodynamics, we can't create or destroy energy, and that we can always transfer energy between systems and all that kind of stuff. So you want to remember that your internal energy is basically a measure of all your energy, and that equals your heat plus your work. And we've used it all throughout the chapter, but what we're focusing on now is it doesn't explain why reactions happen and why other ones don't. So we know that if we take sodium metal and we react it with chlorine gas and we allow them to react, we make salt. But if we have salt sitting on our kitchen counter, it doesn't spontaneously break apart. And the last two sections of this chapter are really dealing with, like, why do some things happen and why some things don't. So that's where we're going. First thing we're going to look at is what does it mean to be spontaneous, and basically if you're spontaneous, it's going to work with it's going to happen by its own accord and without any intervention, and they always happen in a definite direction. So like Humpty Dumpty fell off the brick wall, it always happens in one direction, not the other. So we know if we drop a brick from the top of a building, or letting a gas expand if it's allowed to, letting things rust. So there's different things that can affect spontaneity. Your pressure can affect it, temperature can affect it. We know that if we're below zero, ice is spontaneous, but if we're above zero, then water is spontaneous. So you just keep that in mind when we're looking at different things for that. And here's just an example. We have a piece of metal that's hot, and we put it in water, and we know that inherently the water is going to get hotter, and that's a spontaneous process. Like, we're not going to be able to stop that. On the other hand, for letter B, if we have water sitting in your water bottles that you probably have right now, we know that usually, on any large scale, water does not decompose randomly into hydrogen and oxygen. In fact, we have to run a pretty strong voltage of electricity through it to get that to happen. So the reverse is spontaneous. The forward reaction is not spontaneous. And then when you're at a phase change, like in letter C, when you're at a condensing or a boiling point or anything, that it's actually an equilibrium situation where it's not really spontaneous in either direction. It's stuck in the middle here. So what we're going to look at is spontaneous changes and what makes something spontaneous. And again, the reason why things are spontaneous is because chemicals as a whole are trying to become more thermodynamically stable. Things don't want to be explosive. That's not like their goal in life. So if they can do something to be more stable, they will. And when you do this, you're said to be more product favored. And just because you're spontaneous does not mean you are fast. And you may want to star that, underline it, whatever you need to do. If we build a building and walk away from it for 100 years or so, it's going to fall apart. And that's not a fast thing at all, but it is spontaneous. And think of like spontaneously the Grand Canyon was formed. We did not form it, but it was obviously not a fast progression. So there are some factors that affect spontaneity. We know one thing that's really helps spontaneity is if you're exothermic. So if you release heat, you tend to be spontaneous, because if you're giving off heat, that means your internal energy is lowering, and that means inherently you are more stable. Another thing that helps with spontaneity is more disorder. So if I go from a solid to a liquid or a liquid to a gas, you're getting more disorder in the system, and the universe likes chaos. Like, there is a thing with chaos. So you're good to go with that. And again, we said before, spontaneous processes always happen in one direction. They are not in equilibrium. They aren't easy to go back and forth with. And just like when you drop the egg, you can't unbreak it. Second law of thermodynamics deals with this, and it just says that for spontaneous changes, the universe tends towards greater disorder. So you can tell your parents, I'm not making my room. That is not what the universe wants me to do. And tell them there is a second law that tells me this. There is actually a measure of chaos, which I love, and it's called entropy. And it basically takes the randomness of a system and figures it out. It is a state function. It is a capital letter. So it's an initial state and final state. We don't care about the path. and it is dependent on temperature. One thing you want to underline, remind yourself of, is that it is in joules per mole, and everything else we have done in this whole chapter is in kilojoules, so you have to convert it. I don't know why they put it in joules, like maybe it was just to be mean to you, but you have to deal with the fact that it's in joules per mole Kelvin and not in kilojoules. So there's some ways that you can kind of make some easy predictions about it, and then you can actually do some simple math that we'll look at with it. So what we'll do is just go through it, show you a couple examples, and you will be done with entropy. I will show you can look up entropy values, and again, this is in your note packet. So this is just from a textbook, and like we've talked about delta H. The next section we're going to talk about delta G, but they do give you entropy values. So you can see some things have really low entropy, some things have high entropy. And again, it's in joules, and these guys are in kilojoules, and that is something you have to deal with in your life. That's just the way life goes. All right. So let me move this a little bit. All right, so how do we do some things? If you're getting hotter, typically entropy increases. If your volume's increasing, entropy increases. If you have more independence, entropy increases. So here we have, if you're a pure crystal, you have no deficiencies or anything like that, you have an entropy of 0. So like think of like a flawless diamond would have an entropy of 0 because it would be a pure crystal. More temperature, more volume, more entropy as well. And then you just want to keep in mind that this is a phase change chart. So we have a solid, this is where a solid is. You melt, you become a liquid, you boil, you become a gas. As you move up this chart, your entropy increases, more chaos, more disorder. As you go down the chart, you have less entropy. So we're just going to look at a couple different situations and see which ones are which. So if you look at letter A, we're going from a liquid to a gas. We have more freedom of movement, which means that we would have a net increase in entropy. If you look at letter B, we have an aqueous situation where the atoms can move around, the ions can move around, and they're becoming a solid, which is less freedom. So it would be a negative entropy that we could predict. Letter C is we have a gas on the left side, and we do not have a gas on the right side. So we have less freedom, so we have a negative. And if you look here at letter D, we have 2 gases on the left, and we also have 2 moles of gas on the right. So we can't really make a prediction about that. Our prediction is that it's going to be relatively similar. If there is an entropy change, it's not significant to us. This one asks us which ones do you think would have more entropy just in general. So again, we're looking at different things about it. This one we have salt, that's a solid, and we have HCl, that's a gas. So the gas definitely is more chaotic. It has more freedom inherently. In letter B, the first one is actually more chaotic because there's just literally more of it. So if I have 1 child, not so much. If I have 15 children, more chaos. So same thing goes with chemicals. And then letter C is very close. They're both gases. They're both 1 moles. But HCl just literally has more potential for chaos. It's very close. There's not much of a difference. But because there's 2 atoms bonded together as opposed to just argon, it would slightly have a little more ability to have chaos. And just to show you what you can do if they ask you to do it, you can calculate entropy just like you do with delta heats of formation. So this is where you use that chart, you look them up, same thing, products minus reactants. So we have ammonia, we look up, there's 2 ammonias, we look up, it's 192.5 joules per mole Kelvin, and then we subtract that from all the reactants. So we have 1 nitrogen, and we have 3 hydrogens. And again, you'll end up with joules per Kelvin. Make sure you remember it's joules, not kilojoules. And then really, we're going to use that for something in the last section. We're going to use that for Gibbs free energy. So if they're asking you to calculate entropy, the most likely scenario is that you're going to use it with Gibbs free energy. And if you look at it, it does make sense that this is negative. That means we have less chaos, because if you look here, we have 4 moles of gas on the left as a reactant. We only have 2 moles of gas on the right, so there's definitely more order being created. So that makes sense that there's less chaos in the situation. last thing here is just something that's kind of interesting to know. But when you say that it's not really worth it to clean your bedroom, it actually theoretically in the universe is not, because chaos is always moving forward. However you think our universe was created, since it's been created, has been moving towards chaos. Things degrade and fall apart. So whenever you have a negative entropy change, you are somehow in the universe creating more positive entropy somewhere, somehow. So if you're cleaning your room, you're organizing things. But when you're cleaning it, you're using your muscles, you're digesting food and stuff, and you're actually increasing entropies in other way. So realistically, you never win at organizing. You will always lose the entropy battle because the universe is moving towards chaos. So you cannot win. Sorry. I'm a big organizer, but it's true, we can't win. And then the last two things, you can pause it if you want. Try them. These are just two AP questions that you can see what happens and see if you can figure it out. Alright, so we're going on. The first question, what happens to the cube of ice? If there's no heat exchange, that means the energy is remaining constant. So you definitely want to do that. And what's happening to the total entropy when the system reaches equilibrium, entropy, the ice would melt, which means more freedom. So our entropy would have to increase. What's that one? And last but not least, which of the following reactions has the largest positive value of entropy per chlorine? So you can see like A is out because there's basically the same amount of chaos in both. B is out because we actually have less chaos. C is out because we have less chaos. And then it's between D and E, but it's because it's asking the most positive. And you can see here, we have chlorine here, but we don't have that much. Where comparative to how much other things we have, this one has the most per mole of chlorine. You get the biggest bang for your buck. So that is entropy, and I hope you're almost ready for Gibbs, and then you're done with thermo.